Welcome to my talk on H1 couple length, positive scalar curvature, and low-dimensional aspherical manifolds. So first, I'd like to thank the organisers for this virtual workshop, in particular Christina Sormani. I've enjoyed it very much so far. I think it's been great. I'd also like to acknowledge Misha, who this workshop is in honour of. So, as you all know, Gromov is very famous for many elementary yet incredibly deep observations which lead to very powerful results. In geometry, I am no Misha Gromov, but I hope today I can at least communicate an elementary observation with no claim about its depth or possible strength of results. So let me try to do that. This is a talk on positive scalar curvature. One thing we want to do in Riemannian geometry is ask, how does the existence of certain special metrics restrict the topology of the underlying manifold? So for example, there's this corollary of Meyer's theorem. So you have a complete Riemannian manifold with positive Ricci curvature, then the fundamental group is finite, and it follows that the first cohomology group is 0. So this is a kind of statement I'm talking about. You have a special kind of metric, a metric with positive Ricci curvature, and that gives you some information about the topology of the underlying manifold, namely the fundamental group is finite. Kind of working in the opposite direction, if you just start with a manifold, you ask, can it admit this special type of metric? Well, you can compute its fundamental group. If its fundamental group is infinite, then you know that it cannot admit a metric of positive Ricci curvature. So what about positive scalar curvature? Is there kind of an analogous statement? It's useful to consider this construction. It's a very simple construction. So take any compact manifold you like, M0, and any integer k at least 2. Then construct the manifold, which is the product of your given manifold M0 and a sphere of dimension k. Then this will always admit a metric of positive scalar curvature. The reason being is that you can take any metric on M0 and the round metric on the k-sphere. Now, if you make the k-sphere the radius very, very small, the scalar curvature will become very, very large, and then the overall scalar curvature will necessarily be positive eventually. So you can always get positive scalar curvature on manifolds like this. And note, because of this fact, you can make the fundamental group whatever you want it to be. You can make the first cohomology whatever you want it to be, the second cohomology, second homotopy group. By taking k arbitrarily large, you can prescribe lots and lots of information about the homotopy and homology or cohomology groups. So what this tells us is that scalar curvature, positive scalar curvature, is too weak a condition to provide any restriction on the topology of the manifold, unlike positive Ricci curvature. So instead, I'm going to focus on a family of manifolds, which is obviously not all of them, so it's a much smaller family, which will preclude this type of construction. So namely, these are aspherical manifolds. So a manifold, more generally a topological space, X is called aspherical if its higher homotopy groups are 0. So that is pi k of X is 0 for k at least 2. So note that the construction on the previous slide, M0 cross Sk, would not satisfy this condition. So pi k is non-zero, so that wouldn't be aspherical. So if you have a CW complex, so for example a manifold, then an equivalent characterization of being aspherical is that its universal cover is contractible. So if you have an aspherical CW complex, it's actually determined up to homotopy equivalence by its fundamental group, which is its only potentially non-zero homotopy group. So because of this fact, there's a name given to this space uniquely determined up to homotopy equivalence. It's called a KG1, where G is the fundamental group. So if we now consider not just aspherical CW complexes, but closed aspherical manifolds, then actually the question is, well, could we upgrade homotopy equivalence to a stronger notion of equivalence? So the Borel conjecture would imply, if it were true, would imply that we could upgrade homotopy equivalence to homeomorphism. So that would tell us that if we have two closed aspherical manifolds with the same fundamental group, they're actually homeomorphic. However, the analogous statement for diffeomorphism type is known to be false. So for example, if there are exotic tori in dimensions at least 5. So that these would be there would be examples of manifolds with fundamental group z to the n, two different ones which are not diffeomorphic. They are homeomorphic, but they're not diffeomorphic. This is the class of manifolds that I want to focus on in this talk. So the conjecture, not mine, this is an old conjecture, is that if you have a closed aspherical manifold, then it does not admit a metric of positive scalar curvature. So in order to see whether this is a reasonable conjecture, I want to consider it in low dimensions, so namely dimensions 2 and 3. Dimension 2, we know a lot about. So by the classification of surfaces, every connected closed orientable surface is a connected sum of some number of copies of the 2 torus. So if you take 0 copies, that's just the 2 sphere. If you take G copies where G is positive, then you get a surface of genus G. Note a surface of genus G is aspherical because its universal cover is diffeomorphic to R2, which is contractible. So which of these can have positive scalar curvature? So by Gaspar-Ney, the only possible one which could have positive scalar curvature are the ones for which the Euler characteristic is positive, so that's S2. And we know that S2 does in fact have a metric of positive scalar curvature. So you can see that kind of the opposite of that is that all the aspherical surfaces do not admit positive scalar curvature. So this is saying that the conjecture is true in dimension 2. Okay, so the unique in this case surface which has positive scalar curvature is the one which has precisely 0 2 torus summands in its decomposition. Okay, so in dimension 3 we have a similar statement to the classification of surfaces, but obviously it's more complicated. This is known as the Neser-Milnor theorem. So what it states is that every connected closed orientable 3 manifold is diffeomorphic to a connected sum of prime manifolds, and that these summands are unique up to reordering. So what is a prime manifold? Prime manifold is a manifold which cannot be written as a connected sum in a non-trivial way. So more precisely, if a prime manifold is diffeomorphic to a connected sum, then one of the 2 summands is actually a sphere. So this is known as the prime decomposition of your 3 manifold, this breaking up into connected sum, and can be viewed as an analog of the classification of surfaces. Every closed orientable surface connected is a connected sum of 2 tori. So in this case, instead of just having a single manifold, but 2 torus which generates all of the surfaces, there's a much larger class of prime 3 manifolds. So they come in 3 families. So the first one are free quotients of the 3 sphere. The second is the manifold S1 cross S2, and the third are aspherical manifolds. So these 3 groups can also be distinguished via their fundamental group. So the first one are those with finite fundamental group, the second are those with infinite cyclic fundamental group, and the third are infinite non-cyclic fundamental group. So these are the building blocks for all 3 manifolds, just like the 2 torus is the building block, the unique building block actually for surfaces. But for surfaces, if you think of not just the 2 torus, but the 2 sphere and the 2 torus, then obviously using 2 spheres, connecting some with 2 spheres does nothing. But in terms of the relationship with this 3-dimensional case, it's useful because the building block, which is the 2 sphere, kind of generalizes to the first class of prime manifolds. So those which have universal cover S3 kind of plays the analogous role. Whereas the 2 torus can be generalized in 2 different ways in dimension 3. So the 2 torus is S1 cross S1. So one way you could generalize it to get a 3-dimensional manifold is S1 cross S2. But also the 2 torus is aspherical. So you could also consider the 3rd class of prime manifolds as a generalization of the 2 torus. So in dimension 2, we know exactly which manifolds have positive scalar curvature and which ones do not. And we also do in dimension 3. So this combines work of Gromov and Lawson and Schoen-Yau in the late 70s, early 80s, with Perelman's resolution of the geometrization conjecture. The statement is the following. So if you have a closed, connected, orientable three-manifold, then it emits a metric of positive scalar curvature if and only if it contains no aspherical summands in its prime decomposition. So that is, it only uses the first and second classes of prime manifolds when you write it as a connected sum. So Gromov and Lawson and Schoen-Yau both independently, they showed that if you contain an aspherical manifold in your prime decomposition, then you do not have a metric of positive scalar curvature. So what was left for Perelman, what was unknown until Perelman, was that not containing a spherical factor is sufficient for the existence of a positive scalar curvature metric. So obviously S1 cross S2 has a metric of positive scalar curvature by the construction mentioned earlier, but it's less clear that quotients of S3 have positive scalar curvature. So one of the many implications of Perelman's proof of Thurston's geometrization conjecture is that every free quotient of S3 is actually a quotient by isometries of the round metric. So all these free quotients of S3 emit a positive scalar curvature metric, and then construction due to Gromov and Lawson, also Schoen-Yau, is that if you have manifolds in dimension at least 3 which have positive scalar curvature, then so does their connect sum. So putting that all together, we get this statement. So in particular, a corollary is that if we just look at aspherical three manifolds, then their prime decomposition is just themselves. And this theorem tells us that they cannot admit metrics of positive scalar curvature. So we see the conjecture is also true in dimension 3. Also recently, there was a paper put on the archive last week, actually, by Otis Chidosh and Chao Li, which showed that the 4-dimensional version of the conjecture is also true. Now I want to move on to the Schoen-Yau descent method. So this is a method they developed when trying to answer the question, do tori admit metrics of positive scalar curvature? The theorem I'm referring to is the following. So if you have a closed orientable manifold and a metric of positive scalar curvature, if you take a stable minimal hypersurface sigma inside of M and you restrict that positive scalar curvature metric to the hypersurface, then it is conformal to a metric of positive scalar curvature. So what is a stable minimal hypersurface? So this is the name given to a hypersurface, which when you perturb it in normal directions to get a family of hypersurfaces, the area or the volume of this hypersurface is a local minima in that family, in all possible families, deforming in the normal direction. So this theorem can be interpreted as a kind of hopefully inductive process. If you have a manifold and you want to know, does it emit positive scalar curvature, find a stable minimal hypersurface, then if M has positive scalar curvature, then so does the stable minimal hypersurface. So now the question is, does that hypersurface have positive scalar curvature? And what you've done is you've reduced the dimension of your problem by 1. And then you hopefully can iterate this process. So what's not obvious is how do you find these stable minimal hypersurfaces to get started? So it works as follows. So if you have a degree 1 integral cohomology class, which is not 0, and your dimension is at most 8, then there is a closed orientable stable minimal hypersurface, which is Poincare dual to your chosen degree 1 cohomology class. So why n less than or equal to 8? So this is a combination of two things. So when Schoen-Yau were first considering this problem, it was actually n less than or equal to 7, because the way you get these hypersurfaces is through geometric measure theory. And there, what you can see is that the method that's used to construct these hypersurfaces will have singularities in codimension 7. So if you start with a 7-dimensional manifold and you take a hypersurface, that'll be 6-dimensional. Because the singularity is a codimension 7, it will have no singularities. However, if you start with an 8-dimensional manifold and try and find a 7-dimensional stable minimal hypersurface, its singular set will be dimension 0, but that doesn't mean it's necessarily empty. So the improvement from n less than or equal to 7 to n less than or equal to 8 is due to Nathan Smale, who showed that for generic metrics, a hypersurface will not have singularities. If you have an 8-dimensional manifold and you take a hypersurface, then for a generic metric, the hypersurface will be smooth. So that's why we can improve from 7 to 8. But beyond that, if you take hypersurfaces of higher dimensional manifolds, they'll have singularities. So now if you take another cohomology class, alpha primed, whose cut product with the original one is non-zero, so in particular alpha primed is different than alpha, then when you pull back this new class to the hypersurface, that's non-zero, and you can repeat this process. So you can find a stable minimal hypersurface, sigma n minus 2, inside of sigma n minus 1, whose Poincare dual is the pullback of this form. And then you can kind of move this all onto the original manifold M, and what you see is that this codimension 2 manifold you've constructed is Poincare dual to the cut product of these two degree 1 classes. In particular, this class is non-zero, this homology class. So in general, we kind of just want to repeat this process. So you have degree 1 classes, alpha 1 up to alpha n minus k, with non-zero cut product. And n here is again still less than or equal to 8, so we can get these smooth hypersurfaces. Then if you kind of repeat the process on the previous slide, what you get down to is a k-dimensional submanifold, closed orientable, which is Poincare dual to the cut product of those degree 1 classes. Moreover, at each step, you maintain the property of admitting a metric of positive scalar curvature. So this k-dimensional submanifold will have positive scalar curvature too. This is particularly useful if k is equal to 2, because we know exactly which closed orientable surfaces have positive scalar curvature, and they're just a disjoint union of 2 spheres. So in particular, this homology class, which is non-zero, is in the image of the Horayevich map. So it's just precisely saying that it is given by 2 spheres, can be represented as a map from 2 spheres. So if your manifold satisfies pi2 equal to 0, then this is a contradiction. So remember, this was developed by Schoen-Yau when thinking about tori, which have pi2 equals 0. Tori are a spherical manifold, so pi2 in particular is 0. So this is the method they use to show that any manifold, any torus up to dimension 7 does not admit a metric of positive scalar curvature, because tori have such classes. In fact, it has n of them, not just n minus 2. More recently, Schoen-Yau were able to kind of improve upon their initial paper. So they still use this kind of descent method of taking hypersurfaces and repeating this process, but the way they chose these hypersurfaces was modified in such a way that, so they dealt with singular sets the whole way down, but what they were able to show is that by doing this new construction, the singularities had codimension 3, which meant that if you get all the way down to a 2-dimensional slice, then there are no singularities and you have a smooth submanifold. Okay, and then again, you can apply the characterization of which surfaces have positive scalar curvature. So they were able to use that to show that all tori do not admit metrics of positive scalar curvature. This was also shown by Gromov and Lawson much earlier, similar time to Schoen-Yau's initial paper using Dirac operator methods. So when k is equal to 2, you can get rid of the n less than or equal to 8 restriction. Okay, so now I want to talk about these 1 classes, and I want to introduce a definition to make it slightly easier to talk about. So this is the H1 coupling. Defined as follows. So you have a finite dimensional CW complex like a manifold, and any commutative ring with identity R So this just means that the cohomology will actually have a ring structure. So the H1 cup length of this CW complex with respect to this ring R is the largest integer L for which there are classes in degree 1 which have non-zero cup product. And then denote this by cup 1 sub R of X equal to L. So if you don't require a finite dimensional CW complex, this quantity could be infinite. So you could still define it in that case. But given that I'm only going to be talking about manifolds, it's not really necessary. So just a couple of remarks about this definition. So obviously it's relevant to the previous slide. You just talk about cup length, H1 cup length, rather than writing there exist classes such that. So this is a modification of the definition of cup length, which says that you don't have to have degree 1 classes, just any L classes which have non-zero cup product. So you have a degree 1, a degree 2, a degree 3, several degree 7s, and so on. We just count the number of classes in that non-zero cup product. But all the classes have to have pure degree. You can't have one class being a sum of a 1 and a 3. It has to be pure degree. So if you restrict only to degree 1 classes, then obviously the number of terms in that cup product must be less than or equal to the maximal number if you allow any possibilities. And that's also less than or equal to the dimension. If you have dimension n, then you can have at most n degree 1 classes which cup together to be non-zero. So this quantity is highly dependent upon the ring you choose. So for example, if you consider RPN, the real projective space, then if you use Z2 coefficients, its cup product is n, it's maximal, it's as large as it can be. While if you use integral coefficients, it's 0 because H1 is equal to 0. There is no cohomology in degree 1. But for us, we're really going to be considering just integral or rational coefficients. So if you consider just integral or rational, what you can see is that we have this inequality. So this is because if you have L degree 1 rational classes with non-zero cup product, then after multiplying those rational classes by integers, you can regard them as integral classes, which will still have non-zero cup product. So if you have L of them in rational cohomology, you also have L of them in integral cohomology. But what you don't know is that if you have L degree 1 integral cohomology classes with non-zero cup product, then you necessarily get L rational degree 1 cohomology classes with non-zero cup product. So why can't you go the other way? Well, the problem is integral cohomology doesn't inject into rational cohomology. You lose information, and you lose information precisely when you have torsion. So we could have a scenario where the cup product of these degree 1 classes in integral cohomology is actually torsion. So the degree 1 classes themselves aren't torsion, but their cup product could be torsion. So then if we regarded that in rational cohomology, that would be cup product 0. So an example of this is the three-dimensional manifold, which is the total space of the orientable circle bundle over a 2 torus with Euler number, which is not -1, 0, or 1. Then you can show that the cup product with integral coefficients, the H1 cup length with integral coefficients is 2, but the H1 cup length with rational coefficients is 1, which is strictly smaller. So the idea of what's going on here is you use the Giessen sequence for this circle bundle, and there are 2 degree 1 cohomology classes on the 2 torus. You pull them upstairs to n, then they will cup product together to be non-zero in the integral cohomology of n, but they will be torsion of order E. So when regarded in rational cohomology, their cup product will actually be 0. So using this terminology, we can reformulate what I was saying before about Schoen-Yau's results. Is just purely a reformulation of something they said. There's nothing deep going on here. So if you have a closed orientable n manifold whose H1 integral cup length is at least n-2, and pi2 of that manifold is 0, then M does not admit a metric of positive scalar curvature. Okay, so you have n minus 2 classes, whose cut product is non-zero. That'll be Poincare dual to a smooth surface with positive scalar curvature. So it must be a union of two spheres. But if pi2 is 0, then any map of two spheres into your manifold will be null homotopic and hence can't give you a non-zero homology corpus. Okay, so this is just a reformulation of Schoen-Yau's result using this H1 cut length. So now what I want to consider is what happens if we don't have enough 3-1 cohomology classes? What if we only have n minus 3, we're one short? Can we say something about that case potentially? So there are two issues, or at least two issues that I can see. So the first is that we will need to reintroduce the condition that n is at most 8. The reason being is that in Schoen-Yau's more recent paper, the 2017 paper, their modified method of constructing hypersurfaces produced singularities in codimension 3, which means that if we only have n minus 3 degree 1 cohomology classes, we could get down to a three-dimensional submanifold, which is Poincare dual to the cut product, but that would have a singular set of dimension 0, which is not necessarily empty, so it may not be a genuine manifold. So we know that if n is at most 8, we can use kind of the old geometric measure theory techniques and we'll get a smooth submanifold. But if we remove that condition, even the new Schoen-Yau results don't guarantee that we'll get a smooth submanifold. So that's one problem. So we can just force that new condition, okay, we can reimpose that. But also another complication, which is kind of something that's not trivial how to deal with, is that when we got down to dimension 2, when we had n minus 2 degree 1 cohomology classes, then when we cut them together, which was non-zero, it's Poincare dual surface with positive scalar curvature, that could only be a disjoint union of two spheres. But if you try and do the same thing in dimension 3, then the collection of three-dimensional manifolds with positive scalar curvature is much more complicated. It's not just the three-sphere. But as we saw before, we actually know what they are. So maybe that knowledge is enough. It isn't just one manifold anymore. It's not just the three-sphere. There's infinitely many of them, but we do know precisely which three manifolds have positive scalar curvature. So maybe by analyzing that collection, we can say something. So now it comes to the elementary observation that I promised earlier. So before we get to that observation, just a fact that some of you may or may not know. So if you consider the infinite dimensional length space, which is just the infinite dimensional sphere mod ZP action, so here P is prime. So this is a spherical space. So S infinity is contractible, and we're taking a free quotient of it. So we have fundamental group Z mod P and all higher homotopic groups 0. So it's aspherical with fundamental group Z mod P, so it's a KZP1. So from this description, you can calculate its cohomology. And what you see is that its ZP cohomology is generated by a degree 1 generator, and it's freely generated. So this is maybe more familiar. If you take P equal to 2, then this quotient is RP infinity, the infinite dimensional real projective space. And what changes from infinite dimensions to finite is that, the cohomology ring of RPN with Z2 coefficients is generated by a degree 1 generator. But then you have to truncate it at a certain point because it has to vanish above the dimension. But if you have infinite dimensional real projective space, you don't have to truncate it anymore. You just get the full Z2 generated by X. And something similar happens for an arbitrary prime, not just 2. So that's what this statement says. So it follows from this that an aspherical manifold actually has a torsion-free fundamental group. So why does this follow? So if you have a spherical manifold, and suppose it had torsion, that means that it has a subgroup of the form Z mod P for some P. But that means that there's a covering space by a manifold whose fundamental group is Z mod P. That is actually an aspherical manifold whose fundamental group is Z mod P, so it must be KZP1. So we've got an aspherical manifold, and then we've taken a covering. That covering is again a manifold, but it's a KZP1. However, the cohomology of a KZP1, as we can see, is infinite dimensional. So it can't possibly be the cohomology ring of a manifold. So we get a contradiction. So what we conclude is that the fundamental group of an aspherical manifold is actually torsion-free. Every element generates a infinite cyclic subgroup. Okay, so with this in mind, we can get to the observation. So the observation is as follows. Start with a closed orientable three-manifold, which admits a metric of positive scalar curvature. And let M be an aspherical manifold. So here I'm not assuming that it's closed or orientable, it's just arbitrary aspherical manifold. Then for any map from your three-dimensional manifold into your aspherical manifold, the induced homology class is 0. You push forward the homology class, the fundamental class of Y, you get 0 in the homology of M. So let me try to explain why this is true. So first of all, we know what the positive scalar curvature three manifolds are. They all look like a connected sum of quotients of S3 and copies of S1 cross S2. So in particular, its fundamental group is a free product of some collection of finite groups and a free group, so number of generators. Now let gamma be a representative of a non-zero element of one of these finite groups. So in particular, because it's a finite group, this element will be torsion. Then if we look at the induced element in the fundamental group of M, then that's also torsion, but pi1 of M being an aspherical manifold, pi1 of M is torsion-free, so this element is actually 0. So this element is 0, which means that the map is null homotopic. So in particular, it extends to a disk, the map of the disk. What this tells us is that we can attach a two-dimensional disk to our initial three-manifold Y via the attaching map gamma, and this map F will extend over that attached disk. So if we do this for all of the torsion elements, so for a generating set of each of the finite groups GI, what we obtain is a new space Yi where we've just glued on a bunch of two-dimensional disks. And what this does is it kills the elements of the fundamental group corresponding to these torsion elements. So what we're left with is just the free part. It's just the free part, all the GIs. So that tells us that this initial map F that we started with has to factor through this space. So this space need not be a manifold. We're just gluing on two disks. So it's just a topological space. Note that because M is aspherical, pi2 is 0. So by a similar idea, if we take an element of pi2 of Y1, represented by a map from a two-sphere into Y1, and when we compose it with the map into M, that map is null homotopic and hence extends over a three ball. So we can glue three-dimensional disk, if you like, or three balls onto Y1 to kill all the elements of pi2, and then we get a space Y2 where we haven't changed its fundamental group, but now we've killed pi2. But pi3 of M is also 0 because M is aspherical, so we can do the same thing. We could start with Y2 and then kill all of its pi3 by gluing on four-dimensional disks. Okay, so then the space you would obtain would have the same fundamental group, pi2 would still be 0, but now you've killed pi3. Pi3 is also 0. You can just keep doing this. So if you repeat indefinitely, what you see is that your initial map that you started with, no assumptions on that map, it's just a continuous map. It has to factor through a space called Y sub infinity, where the fundamental group is the free group on M generators, and all the higher homotopy groups is 0. So each stage we're killing another homotopic group. So in particular, this space is aspherical. And its fundamental group is the free group on M generators. So we're just gluing on disks. So this is a CW complex. So it's uniquely determined up to homotopy equivalence by its fundamental group. So any other space, any other aspherical space with the same fundamental group has to be homotopy equivalent. There's a particularly nice space with that fundamental group, which is aspherical, which is just a wedge of M circles. So it's a bouquet of circles. So we see that this space, Y infinity, is homotopy equivalent to this bouquet of circles. But this bouquet of circles is just a point with several loops wedged together. There is no three-dimensional homology. So the three-dimensional homology is 0. It's a one-dimensional CW complex. So our map from Y to M has to factor through this space, Y infinity. So on the level of the induced map of H3, it has to factor through the group 0. So that we see that when you push forward the fundamental class of Y, you must get 0. Okay. So this is kind of hopefully suggestive that this could potentially be used to answer the question, what happens when you have H1 cup length n minus 3? Because there, one of the problems was the Poincare dual of the cup product of n minus 3 degree 1 classes is represented by some positive scalar curvature 3 manifold, but there are lots of different ones. So one thing we can say is that, well, if you're on a spherical manifold, then you can't represent degree 3 homology by a positive scalar curvature manifold. This is what this tells us. Because any map from a positive scalar curvature 3 manifold into an aspherical manifold must be 0 on H3. So it's hopefully going to allow us to answer that question. So here are some results. So before getting to that, what happens if you just take your aspherical manifold to be three-dimensional, just like your Y? So suppose M is closed, orientable, and three-dimensional aspherical manifold. And Y is again closed and orientable and admits a map of non-zero degree onto this aspherical manifold. Then you can see that Y does not admit a metric of positive scalar curvature. Because being of non-zero degree means the map on H3 is non-zero. But as we just saw, any map from a positive scalar curvature 3 manifold to an aspherical manifold has to be 0 on the level of H3. So you get a contradiction. So this statement makes me want to just remind you of the conjecture that I posed at the beginning. So initially I didn't have the word orientable here. So I just said a closed aspherical manifold does not admit a metric of positive scalar curvature. But obviously if you can answer it for orientable, if you can prove it for orientable manifolds, then it follows for all manifolds, because if a non-orientable manifold had positive scalar curvature, so would its orientable double cover. So it's enough to consider orientable ones. But I want to also extend this conjecture. This isn't due to me either. It's just, I want to mention it now. So suppose you don't only consider closed orientable aspherical manifolds, but those manifolds which admit non-zero degree maps onto such manifolds. So in the language of Gromov, we would say that N dominates M. So that is, N admits a map of non-zero degree onto M. So conjecturally, not only do closed orientable aspherical manifolds fail to admit metrics of positive scalar curvature, the same is true for any manifold which dominates such a thing, that is, admits a map of non-zero degree. So what the above corollary tells us is that the conjecture is true in dimension 3. Conjecture is also true in dimension 2 for much more trivial reasons. So the only way it could be false is if you had a positive scalar curvature surface, which admits a map of non-zero degree into an aspherical surface. So this would be a map from S2 to some aspherical surface, some surface of genus G, which has non-zero degree. But because S2 is simply connected, well, not even that. So any map from S2 to an aspherical manifold is 0 because it's an element of pi2. So dimension 2 is easy, and the above corollary shows it's true for dimension 3. So I mentioned earlier that Chodosh and Lee showed that the initial conjecture, where I didn't ask about domination, or this more general conjecture, they showed it was true in dimension 4. I haven't read that paper in detail. I don't think, please correct me if I'm wrong, I don't think that that paper allows you to show that this more general conjecture is true in dimension 4. So I think the statement of if you have a 4-dimensional manifold which admits a map of non-zero degree onto a 4-dimensional aspherical manifold, I don't think that paper addresses whether or not that manifold has positive scalar curvature, but I may be wrong. I'd be interested to know if anyone wants to correct me. Okay, so we know it's true in dimensions 2 and 3, but I believe it's still open in dimension 4, this more general form of the conjecture. So now I'll finish up with some results. So here, M and N on this slide will be closed orientable n-dimensional manifolds with n at most 8. So we need this n at most 8 condition to get smooth hypersurfaces in these dimensions, and to use the theorem. If we could improve the Schoen-Yau kind of technique to get rid of singularities in dimension 3, then we could remove this restriction. So there are 2 theorems. So before stating these theorems, let me just say in the proof of the observation, we kind of went a bit overboard. We killed, we removed the torsion of pi1, we constructed this new space y1, and killed pi2, pi3, pi4, and so on indefinitely. That allowed us to identify what this space y infinity was. Exactly, it's a wedge, up to homotopy, it's a wedge of circles. But that isn't necessary to deduce the statement. To deduce the statement, all you need is that 0 on the level of degree 3 homology. So actually it's enough just to kill pi2 and pi3. And actually you can show by cellular approximation and so on that that's enough. You can just kill pi2 and pi3. So that's why in these statements here, you're just seeing pi2 and pi3, you're not seeing higher homotopy groups. So theorem A says you have a manifold which has cup length at least n-3. Pi1 is torsion free, and pi2 and pi3 is 0. So if you're in a spherical manifold, these conditions on pi1, pi2, and pi3 are true, but you don't need the assumptions on higher homotopy groups. So if you have such a manifold, M, and then your manifold N admits a map of degree 1 to such a manifold, then M does not admit a metric of positive scalar curvature. Theorem B is stated slightly differently. So there's a different set of hypotheses. So here now the H1 cup length with rational coefficients is at least n-3. And now pi2 and pi3 are also assumed to be 0. So then now if you have a manifold which admits a map of any non-zero degree onto M, then that manifold does not admit positive scalar curvature. So let me just highlight the differences between these 2 statements. So obviously the first one is that in theorem A, we have integral H1 cup length, and in theorem B, we have rational H1 cup length. So if we have integral H1 cup length, what this helps us in 2 ways. So the first way is that it allows us to get rid of pi1 of M being torsion free as a requirement. The reason being is that because the H1 cup length with rational coefficients is at least n-3, that means that there are n-3 degree 1 rational classes with non-zero cup product, which means that if we multiply that cup product by any integer, it will remain non-zero, whereas that's not true if we just work in integral cohomology because the cut product could be torsion. So what is the effect of multiplying the cut product by an integer? It means that we don't have to represent the Poincare dual of the cut product. We can just represent the Poincare dual of any multiple of the cut product. So what does this mean for the three-manifold? This means that I can, instead of looking at the three-manifold, I can take any finite cover of that three-manifold. So a degree D finite cover, that three-manifold will lead to multiplying the degree 3 homology class by D. So in rational cohomology, that will still be non-zero. But if you were to use integral, then we wouldn't know for sure that that is non-zero. So how does the covering space help us in this theorem? Well, it's a fact of three manifolds. It's not too hard to show that if you look at the set of positive scalar curvature, three manifolds that are all connected sums of quotients of S3 and copies of S1 cross S2. So if you can show that every such manifold of that form has a finite cover, which is just a connected sum of S1 cross S2s. You don't need any spherical quotients. So after passing to a finite cover, you can just use S1 cross S2s. So that's what helps us in the rational case, because we can just assume that we're working with a three manifold, which is just a connected sum of S1 cross S2s. So in particular, the fundamental group of such a manifold is already torsion-free. So we don't need to assume that the manifold we're mapping to, M, has pi1 torsion-free, because we wouldn't need that condition. We already have a torsion-free three manifold representing our homology class. So that's one way. Also, it allows us to replace degree 1 with non-zero degree, because because we have a homology class in degree 3, which when multiplied by an integer remains non-zero. Whereas in the integral case, the only way you can ensure that it remains non-zero is if you multiply by 1 or minus 1, which is why we have degree 1 in theorem A. Okay. Let me finish up by saying the corollary of theorem B is that if N is a closed orientable four manifold, which dominates an aspherical four manifold with B1 positive, so remember dominates means admits a map of non-zero degree, then N does not admit a metric of positive scalar curvature. So this is a partial result towards the strengthened conjecture in dimension 4. It's obviously not complete because there exist aspherical four manifolds with B1 equal to 0. So there are even integral homology spheres which are aspherical due to Ratcliffe and Shands. So this is far from completely answering the question in dimension 4 for that version of the conjecture. I should mention that the non-existence of positive scalar curvature metrics on closed aspherical four manifolds with B1 positive appears in Wang's 2019 thesis. So the idea is pretty much the same, just the implementation is different. So he uses immersions and argues that you can kind of break up an immersion to separate the connect sums into a disjoint union, and then argues kind of similarly. I think the argument I used with homotopy is a bit more robust. So I also think he didn't consider higher dimensional aspherical manifolds, but the idea is basically the same. So I just want to end with a question which I would like to know the answer to, and I'd be happy if anyone could answer it for me, is whether we can remove the condition on the dimension. Can we remove the condition that n is less than or equal to 8? So remember, the problem is that when you get down to the three-dimensional slice, this kind of repeated slicing of hypersurfaces, even if you use the new Schoen-Yau, you have a singularity set which is zero-dimensional, but not necessarily empty. If we could show that it was empty, then we could remove this hypothesis. So what this kind of may remind you of is that in the initial Schoen-Yau, kind of the early Schoen-Yau paper, they were using geometric measure theory where the singularities had codimension 7. And then there was this result of Smale which said, well, for a generic metric, you can get rid of the singular set when it's zero-dimensional. So if you had an 8-dimensional manifold, hypersurface, its singular set would be zero-dimensional, but then Smale's result says if you are willing to perturb your metric a little bit, you can get rid of those singularities. So maybe there's kind of a souped-up version of Smale's result, which would say, for this new technique that Schoen-Yau have implemented, for a generic choice of metric, it's not just that the 2-dimensional slice is smooth, but actually the 3-dimensional slice is smooth, that you can kind of perturb away these zero-dimensional set of singularities. But that is far from obvious, and I don't know if that's true. If anyone has any thoughts on that or any other aspects of my talk, I'd be glad to discuss them. So thanks for listening.